Now let's talk about spacing. For spacing, all agents will rotate around a common circle. First, let's look at the simulation. We have 4 agents. Each of them moves in circular motion. You see, all of them are coming towards the center circle, and eventually they will circle around the same center with the same radius. You say initially all the agents. If you still remember that we do the simulation for synchronization, balance configuration, and spacing. So for all the 3 different cases, the agents have the same network topology, the same initial position. The only difference is they use different control laws. You see, for this blue agent, it come toward the center to the green one, and this agent 2, see, eventually they circle around the same center with the same radius. Now let's talk about how to achieve such behavior by using distributed control law. So for spacing, first let's know that if we give a constant control input for the seat I dot t, so if we give each agent a constant control input, then the agent will be, the motion will be in a circle. So how to see this? We can calculate, we know xi dot. If seat I dot t is u0, then we know, so the seat I t can be reached as 0t, then plus some constant, okay? So without loss of generality, let's assume the constant 0, okay? Then we know x dot t is normalize the velocity. So ct, we integrate both sides, we have xit, xi0 from 0 to t. So cosine seat I, so seat I will be u0 tau d tau. Okay, so then xi t will be xi0t. Then we can d tau, we can be written as d u0 tau. Then we have u0, 1 over u0 in front. 1 over 0. Then we have sine u0t plus 0, sine 0, 0. Okay. Then for yit, we can do the same thing. It will be yi0, 1 over t. Now we have 0t sine u0t okay, d u0t would be minus, okay, minus cosine u0t, then minus 0, cosine 0 will be 1, is minus 1, okay, then we plus u0, okay. Then from this part we know, so the agent, if we use xi minus xi0 square plus yi t minus y0t minus so it should be 1 u0 square. Then you know it's a circle, okay? This is the center. So that should be the circle. The radius is 1 over u0 absolute value. So the agents are moving in a circle if we give a constant input u0 for c dot, if c dot, if sit I dot, sit I dot is u0, it will be in circular motion. Then what's the center? We can use the center. We just showed where the center is, but I can show you a different way how to calculate the center. Let's have the coordinate. Okay. Suppose this is R, where the agent is no R. So RIT will be XIT plus JYIT. The position of agent. X coordinate XIT, Y coordinate is YIT. Then we know the velocity. We assume the velocity is a constant. Okay, so it will be 1 normalized, because let's assume theta is the velocity, so it is 1. Okay, then we have theta I. Okay, then we know, so this one is the r dot. Yeah, so r dot is exponential. We have this dynamics. So remember, we have ri dot is exponential j theta I. Okay, so that should be the r dot, where the r is going to be. Then we can times the j. If we times j, it means it's move the counterclocks direction by 90 degrees. And we know this radius. The radius of it is 1 over u0 square. Okay. It depends on which direction. Okay. Okay. It maybe go in this way. It depends on the sign of u0. If it's positive, we go this direction. Then it will be the center. Okay. This will be the center. So the center of C, this will be CIT, is the center. We know it will be RIT plus J. Therefore, center will be RIT. will be then plus this vector, okay? J times, here's no J, then here's J times exponential J theta I is in this direction. So the radius is 1 over u0 squared, no absolute value, okay? So then we know the agent will be travel in a circular motion with the center, here's the center, and this is the radius. So for all the agents, they will travel around the same center. Basically, we want them to have common value of CIT. Then this is the CIT. To have a common value of CIT, so we can design another variable. We call it J minus J U0. Then this we call it QIT. So QIT, let's multiply the CIT by minus J U0. So for the RIT, we have minus U0 RIT. So then the U0 is cancelled. For minus J square is 1. So has exponential J theta I. Okay. Then we can define a Lyapunov function. We call it potential function. Then L is the Laplacian matrix. Then we need 0. So when, let's say we have Q, sorry, I should have Q. So VQ is 0, basically it means all Q belong to spine of all one vector. Okay? Means all Q is same. Basically means all agents, they have the same center. Since they all use, so we use 0, so they have same radius. Okay, you have the same center, same radius. Okay, they rotate around the common center. Then how to achieve this part? We know we need to minimize the VQ. To minimize VQ, then we can calculate the gradient direction. Then we can take a minus of the gradient direction, so we'll multiply by the gradient direction, say partial V, partial theta I. Okay, this will be partial V, partial theta I. Then the U0 is a common, so it's a common term. Then the second term is to achieve the consensus part by considering neighbors information. Okay, now let's calculate. So partial V, so partial theta I, as we showed last time. Okay, so the partial V, partial theta I can be written as the real part. Okay, the real part of partial Q, partial theta I. Then we have times Q. Okay, so this is what we have been shown last time. Okay, then it will be equals to partial. So partial Q, we know the definition of Q here. So it has two parts. Okay, so for the partial Q, so this one is not reduced theta I. Okay, so for the first term, it will be J exponential J theta I. Okay. Then for second term, we can separate. Okay, we can have L I. So minus Li, so J U0 Ri. Okay. So it will be the real part of j ej theta I. So Li ej theta I minus the real part of j ej theta I, then Li j u0 ri. Okay, so this part, okay, we have talked about this part in the previous lecture. Okay, so this is just here. Okay, this we talk about like last lecture. When you calculate this part, it's exactly here. Okay, now we need to focus on the second part. Okay, so let's erase it. Now we only need to focus on the second part. Okay. Then for the second part, okay, we can have, let's say, let's copy it here. We have j exponential, then the j, we can move j here. Then we have I, we have u0, okay? I put u0. Then here's not, let's say here's r, okay? Sorry, here's r. Then we have the sum, okay? Okay, sum r from, I think we have j is k from ni, have r I minus rk. Okay. So then we have j. Then if we move this j out, is the sum. Okay, then we move this j out. Okay, we minus j squared to u0. This is the sum part. See, this is 1. Okay, then we can move u0 out to be u0 minus e theta I, and this is the sum part. Yeah. Okay. Then the u0 here. Okay. Now let's only calculate the real part of exponential j theta I, then sum, so k down to ni, xi, so ri minus rk will be, let's just calculate. Okay, we can written as in this form, the real part. Then let's see so here it will be cosine theta minus j sine theta I. Okay, so here part, let's just take 1. Okay, let's take k. Okay, so it will be xi minus xk plus j yi minus yk. Okay, so the real part will be just, okay, cosine theta I xi minus xk. Okay, we have cosine theta I xi minus xj, then we have minus sign here, so it will be xk minus xi, so it will be xj minus xi. Okay, then for we have real part, we have this term times this term. Okay, you see we have minus qj squared, so it's 1. Then we have sine theta I, so yi minus yk. But again, we have minus sign here, so we have yk minus yi, here's yj minus yi, I have sine theta I. So this is q, sorry, this is typo, should be q. Now, so this part will be just partial VQ, partial theta I, and Q is less than 0 to minimize V theta. So this, the constant term, so this is for reach consensus, okay? Reach the same circle. Okay? It's basic the control law by using neighbors information to achieve consensus on rotating on the same circle. So that's all about formation control.